Hello, and welcome to Summarize Science, where we break down complex research for everyone. Today, we're looking at a fascinating paper that could change how we fix damaged or low-quality images. Powerful AI tools called diffusion models are great at tasks like deblurring a photo, but they have a major drawback. They're extremely slow, often requiring hundreds of steps to produce a final result. Newer consistency models were created to solve this speed issue, enabling image generation in just one or a few steps. However, directly using these super-fast models to fix a specific corrupted image has been a challenge. This paper introduces a new approach called measurement-guided consistency sampling to bridge that gap. So, how does it work? The core idea is to cleverly guide the fast consistency model during its generation process. Think of it like a detective sketching a suspect from a very blurry security photo. The detective starts with a rough guess, but then constantly compares their drawing back to the blurry photo. This diagram illustrates the process. The AI generates a potential fix, which is then compared against the original blurry image, creating what's called a measurement residue. This residue, or error, tells the AI how far off its reconstruction is. If the error is large, the system introduces a bit of randomness to explore new possibilities, like the detective making a bold change to their sketch. But as the generated image gets closer to matching the blurry photo, the process becomes more stable and deterministic, making only fine-tuned adjustments. This smart feedback loop ensures the final image is not only high quality, but also faithful to the source measurements. But does it actually work better? The researchers tested their method, which they call inverse DDM, on several tasks and datasets. Here you can see the results for super resolution, deblurring, and inpainting on complex bedroom images and simpler fashion images. In these visual comparisons, the proposed column consistently shows results that are sharper and more perceptually realistic than the baseline method. The quantitative results in tables 1 and 2 confirm this. Across the board, the new method achieves better scores on metrics like FID and KID, which measure how realistic an image looks to a person. Interestingly, for the more complex dataset, the pixel-perfect scores were sometimes slightly lower. The authors suggest this is because their model is better at hallucinating plausible details, which look great but don't perfectly match the original pixels. This highlights a classic trade-off between strict accuracy and perceptual quality. So, to recap the key points, older AI methods for fixing images are powerful but slow. Newer consistency models are incredibly fast, but aren't tailored for these reconstruction tasks. This paper introduces a measurement-guided method that combines the best of both worlds, using the error from the corrupted image to intelligently guide the super-fast generation process. The result is a system that can perform high-quality image reconstruction in just a handful of steps. This could lead to much faster and more powerful tools for real-time video enhancement, medical image analysis, and everyday photo editing software. That's all for today's episode of Summarize Science. Thanks for watching.